Welcome back. So in this lecture, I'm going to give you a very high-level overview on what forces are, the different types of forces, the strategy for it, and everything to do with forces. So up to now, we were describing motion, right? That's what kinematics is. We were describing motion. And how do you describe motion? Well, you can talk about the displacement of the object, the velocity, the time, the acceleration. And if you don't know those variables, then you can use the kinematics formulas to figure out the remaining variables. That's kind of what we were doing so far. We were describing motion. What we're going to do for the remainder, essentially, of all these physics videos is we're going to talk about forces. And what is a force? A force is what's causing this motion to occur, right? So if I'm walking down the street with some displacement and some velocity, the reason I am moving is because I'm putting a force on myself. Or if I'm driving a car, the reason that car is moving is because we're exerting forces on that car. So really, the first couple chapters of most physics classes talk about describing motion, but what's causing motion is forces, and that's really the remainder of physics. So it's really good idea to get an intuition on what forces are, since we're going to be dealing with it for at least 6-7 chapters. It's going to come up in many different ways, and it's truly one of the most fascinating concepts in our universe. So I'm very excited to talk about it. So forces are causing motion. But if we really need to describe, really put a definition, what is a force? Yes, it's causing motion, but a force, the formula for force is mass times acceleration, right? It's a pretty simple formula. It's mass times acceleration. But if we think about what this intuitively means, this mass times acceleration, what it means is whenever you have any mass and that mass is accelerating, then you have exerted a force. So a force is something that not only causes motion, but it more specifically causes a mass to accelerate, right? So it doesn't just cause a mass to have a constant velocity. That's not what a force is. That object actually has to accelerate for it to be considered a force acting on it. So that's kind of a subtlety of forces, but I want to really hit this home. This is kind of a generic way to think about it, that they cause motion. But more specifically, a force is anything that causes a mass to accelerate. And that's why the formula for force is mass times acceleration. So it's a subtle formula, but it's profound, but it's rather simple in that sense as well. So many profound things in the universe are relatively simple in this sense, but it's simple and profound at the same time. So just to really hit it home, I wrote it in words that anytime you exert a force on an object, that object should accelerate. So just keep that in the back of your head. Whenever you're thinking of force, think that object needs to accelerate. Now, so let's give an example just to hit it home, right? So let's say you have a car, and that car is emitting fuel out of its back here. That means that fuel is going to exert a force forward. And if I'm exerting a force on this car, then that means this car is going to accelerate, like so, in the x direction. So it's going to move. Now, you're going to notice in a lot of these problems that sometimes the object is not moving at all, right? So let's say I have a person who's just kind of standing on the ground, and the person is not moving at all. So you might be tempted to think, oh, there aren't any forces acting on this object, because if like Nauman said, my name is Nauman, by the way. So like Nauman said, right, if you exert a force, the object should accelerate. Since this person is not accelerating, there are no forces. That's kind of how I used to naively think about it when I was first learning physics. But there's actually, if an object is not moving, that means there's actually multiple forces acting on it, and the net force is 0. So what do I mean by that? Well, it doesn't mean that there aren't any forces. It means that there's actually, let's say, a force of gravity pushing down on the object. And because I'm standing on the ground is actually exerting an upward force as well to prevent me from sinking into the bottom of the earth. So there are actually two forces going on in this problem. There's a force of gravity going down, and there's a force from the ground pushing up. So I'll write force of ground, and force G just means gravity. So each of these forces, force of gravity, would cause this object to accelerate if there was nothing else in the way. But since we have the ground in the way, that's going to push back up. So your net force, your overall net force is 0, and that's why your object is not moving. If your object is moving, like in this example, right, there is movement, then what is going to be your overall net force? It's going to be the mass times the acceleration, because any force is mass times acceleration. So this might not make complete sense right now, but we're going to do many, many, many problems. Trust me on this. We're going to do so many force problems that it will definitely make sense. So this is just to give you a high-level overview of what's going on. So the nice thing with forces are there's pretty much a consistent strategy you can use for every force problem, because I love having a strategy and having a game plan when I see a problem rather than just kind of winging it. So what is that strategy? Well, the first step is draw all your forces out. So you might have only one force, as in this problem. You might have 2 forces. You might have 5 different forces acting on an object. The first thing is draw all your forces. The second step is anytime a force is a 2-dimensional force, you want to split it into x and y. So just like kinematics, anytime you see something 2D, break it into x and y. Anytime you see something 2D, break it into x and y. And again, what is a 2D force? It's a force that's not entirely in the x or y direction. So here this force is entirely in the x, and these two are entirely in the y. But if a force is, maybe a wind is blowing this way, like at this angle, that is a 2-dimensional force which you would need to split into its x component and its y component, like so. So any 2-dimensional force like that, immediately, before you do anything else, just split it into x and y. The next step is you want to add up all your forces in x and y separately. So you want to treat x and y completely separately. Again, just like kinematics. So if you think about it, it's very similar to kinematics, right? Because in kinematics, what did we do? We drew a picture of what was going on. Anything that was 2-dimensional, we split into x and y. And then we looked for our 6 variables: acceleration, v initial, v final, initial x, initial y, final x, and time, and we did them in the x and y separately. So same kind of strategy. And the last step is to figure out what is the overall net force, right? Because if I have an object and there are multiple forces acting on the object, I want to figure out what is the overall net force. And there's only 2 options, right? If the object is not moving, then your overall net force is going to be 0. And if your object is moving, your overall net force is equal to the overall net force, which is m times acceleration. So that's kind of nice. There's only 2 options. Either it's going to equal 0, or your overall net force, you'll have one, and that'll equal ma, because any force is just mass times acceleration. All right, now let's talk about the different types of forces you can exert on an object. And so obviously in the universe there are hundreds of different forces, but we're going to keep it pretty simple here and talk about the main ones that we talk in a general introductory physics class. So the first is this mysterious force of gravity that exists in the universe, right? Gravity is just this mysterious force. People have spent many years trying to figure it out, and to this day it's mysterious that this force of gravity kind of just causes things to accelerate downward. So basically every single problem will have this force of gravity in it. Another force is a force exerted by contact. So what do we mean by contact? Well, anytime you're literally in contact with something, like you're touching, let's say, a floor, a wall, or really anything, if you're in contact, that's called a normal force. So if we go back to my ground problem, right? This person is in contact with the ground, so therefore the ground is exerting a force up. So when I wrote force ground, I could have also written normal force, F, and then an N on the bottom. So normal force. And there's nothing normal about this force, so I truthfully don't know why we call it normal force, but that's just kind of the name that's given. And even actually, if we go back to this problem, we can add more forces now, right? So this was kind of an incomplete diagram. If you really think about it on this car, you have that fuel is being emitted and it's exerting a force in the x direction, but there is also gravity acting on this car downward, and since the car is in contact with the ground, there's also going to be a normal force pushing up. So look, it seemed like a simple problem, and we've already drawn 3 different forces going on. So this, let me just label it. This would have been your force due to gravity. This would be your normal force. All right. Another force you can have is a force that is opposite to the direction of motion, which is your friction force. So let me clarify what I mean by all this mumbo jumbo. So if I have let's go back to my car. So let me change colors here for a sec. All right, let's go back to this car. So, and let's also label this. This is the force from the fuel, right? So I didn't put fuel as one of the types of forces because when I mean types of forces, I mean the things you wouldn't kind of normally maybe necessarily think about. Fuel is just kind of this extra thing that we're adding in here. So, right, some of the basic forces, if I poke this guy, that's obviously gonna exert the guy forward. So I didn't write poking as a force down here. So you can always add fuel or poke someone. Those are kind of more common sense things. The types of forces I'm thinking about are maybe necessarily things you wouldn't necessarily think about. Like I would have never thought that the ground actually exerts an upward force, but now you know. So there's gravity, which exists. There's this normal force, and now we're going to talk about friction. So friction is always opposite to the direction of motion. So if I'm going to the right, then that means there's actually a friction force going to the left. So I would write force of friction going to the left. Okay, so if I'm going to the right, the friction is to the left. And you have to have contact with some surface to have friction, right? So if you think about it intuitively, you can't just if I have a ball that's in air and the ball is just going to the right, I wouldn't say there's a friction going to the left because it's not in contact with any surface. So maybe I should have added that in here, that it's an opposite to direction of motion when you are in contact with some surface. So let's elaborate a little bit more on this friction force, right? Why do we have this friction force in the first place? And the reason we have this force pushing to the left, because this always used to confuse me, right? I was like, okay, there's a car and the car is sitting on the ground, so it makes sense that the ground is kind of pushing up on this car. That I understand, that the ground, this blue line, is pushing up and exerting this force. Otherwise, if it wasn't, the car would just be sinking down. That I bought. But it always used to confuse me that how can the ground, which is this straight line here, push something to the left, right? I mean, it makes sense. Okay, I'm pushing up, I got that. But how is this thing on the ground pushing something to the left? It just used to mind boggle me. And let me just elaborate on why that happens for a second, in case it's confusing you as well. So the reason you can push to the left like this is because even though we're drawing the road as a straight line, if you really zoom in on this road and look at it, like, you know, take a microscope and really zoom in here, it's really not a straight line. If you really look at what a road looks like, so let's draw this down here. I need a little bit of room. So if you really look at what a road looks like, or any surface for that matter, it's not this smooth line that we're kind of quickly drawing on these pictures. If you really look at it, right, it's kind of bumpy. So here's my road. Okay, let me finish drawing all my bumps. All right, and there we go. Let's draw some more. Perfect. Okay, so, and let me get my car out. So let's switch colors, and then let's say here's my car. Okay, this is what a road actually looks like, or any surface for that matter. Looks kind of bumpy when you really zoom in on a very microscopic level. It's kind of bumpy. So yes, when gravity is pushing down on this car, these bumps are going to push up. But when I want to go to the right, I have to overcome all these bumps, right? So you can imagine this bump right here is going to be like, I'm not letting you go to the right, and it's going to that bump right here is going to push to the left, and so are these bumps around it. All these bumps here are going to kind of push to the left. So these bumps down here are what's pushing up for that normal force. But when you are starting to go to the right, it's these bumps here that are, since it's not a completely smooth surface, it's going to kind of push it to the left. So that's why you have this friction force, because it's not really a straight line. If it was truly completely smooth surface, then you wouldn't have a friction force. But since it's kind of bumpy like this, those bumps push to the opposite of your direction of motion. And it's not just a road, right? It's actually every surface on Earth. Think of like your desk, right? You might think, oh, my desk is very smooth, so maybe my desk does look like a line. But even your desk, if you really zoom in on a particle level, it's bumpy. So pretty much everything on Earth, even I would say the smoothest thing is probably ice. You could probably argue that if what am I doing? Ice. I can't even spell. All right, ice. If I'm on a surface of ice, you can imagine that's probably one of the most smoothest things. The fewest bumps are in ice, but even ice probably has very small amount of friction. So truly nothing in the universe is completely smooth and has no bumps. So that's just something to keep in mind. Now, that being said, you might be given problems where they say there is no friction. Assume a frictionless surface. So if they say that, they're saying assume that it is this nice straight line, when in fact, in reality, everything is bumpy. So if they say assume there is no friction, then you can say friction is equal to 0. But the reason they'll say that is just to make the problem easier for you. In reality, nothing has 0 friction, but they might just kind of say that to make it simpler. So, watch out. If you have 0 friction, that's just because they're being nice. But in reality, you always want to assume that when you're in contact with a surface, you will most likely have a normal force, and you'll have this friction force going on. And what is that friction force? Since we're spending all this time on friction, I might as well just tell it to you. That friction force, that the force due to friction is mu times the normal force. So friction force, how much friction is exerted, is dependent on the material you are on. So if you really are on a bumpy road, you can imagine that bumpy road is going to have a lot of bumps, and those bumps are going to exert a higher friction force. Versus if you're on ice, it's going to be a relatively smooth surface, and so you're going to have a much lower friction force. So mu is going to depend on the material you're on, and it'll always be given to you. If it's not given to you, then they're going to ask you to figure it out. But generally speaking, mu is basically it's a coefficient that's basically saying what material are you on. So if you're on a very smooth surface like ice, you'll have a lower mu. If you're on a very bumpy surface, you'll have a higher mu. And right, if I have a higher mu, that's going to give me a higher force of friction. So that makes sense, that if I'm on a very bumpy surface, I expect higher friction. And then you multiply it by the normal force. And that's pretty interesting, that the friction force is related to this normal force. Even though normal force is pushing completely in the y direction, it is somehow related to that. So I want you to get the intuition on this formula, because if you just memorize it, that's fine. But if you have this intuition that it depends on this normal force, that's going to come in handy a lot later, because you can imagine, right? I said we need to add up all our forces in x and y separately. But if this is a force that's acting in the y direction, and this is a force that's acting in the x direction, then once you figure out what the normal force is, you can use it to get friction. So we're going to show that in problems in the future, but I just want to give you that heads up now that we're going to use forces in the y side to get forces in the x side, and vice versa. And this is one of those times we're going to do that. All right? So that is your friction force. And the last force is any force in a string or rope is called a tension force. So again, so let me just draw that out. Let's say you have a yo-yo, and that yo-yo is hung up by the string. So the yo-yo will have a mass, and that mass is going to exert its own force due to gravity down. But then the tension, the string will pull it up. So instead of saying force of string, I'll say force of tension is going to pull it up. And again, there's nothing, sorry, that's not a very clear T, but there it is. There's nothing, I don't know why they call it tension. It doesn't really cause, tense or stress or anything like that. It's kind of like normal force. It's just, it has a weird name. So when you think tension, just think a force in a string or a rope that's kind of pulling on an object. All right? So this video is meant to give you a very big picture overview. In the next videos, we're actually going to apply all this. We're going to look at the strategy. We're going to look at different forces and see what we can come up with. All right.